did it a straightforward way? And do you have a method that you used?
No.
Pretty straightforward. And what method did you use, Kevin?
Shell.
Shell. Okay, so for shell. It's frozen again. Work with me. Okay. Does anybody feel like if things didn't go wrong, they could be more of a Mary than a Martha? But things go wrong, then you have to be a Martha. Okay. Okay, coming back. That's a hard story because in some ways it's like, but you gotta get stuff done. Anyway. But in other ways it's like, okay, but what's your heart posture? What's your mind? And then you look at Mrs. Leon, who is highly efficient and yet never stressed. Well, in physics, I'm sure there are times that she's perplexed and maybe somewhat frustrated. Someday I'll grow up.
Are these? I've never seen her.
We had a good conversation going to Starbucks right before Starbucks.
She has so many.
I got stressed out when I got my stupid corks.
Yeah, so not saying she's never, right? She's human. She would admit that as much as anyone else. But just her heart posture, even though she's highly efficient. Okay, put me back. Para-shell method, right? Did you slice it this way?
Yeah.
Did you go straight to plugging in, or did you visualize it all? I'm just asking. Okay. If you went straight to plugging in, you're like, okay, well, it's a dy, right? Para-shell. Okay, a dy. So it's like, okay, I don't know exactly what I'm doing, but I do know that I'm doing a 2 pi integral with a dy, and I need an r of y and h of y. And did anybody realize that whenever you're doing it in terms of, it's always a y or a y minus? Guys, how big is the radius? Is it a y minus or is it just a y? Because you always go from the axis to the representative and, it's at 0. So top is the y and bottom is 0. Just y or y minus 0. Times, going the other way. I have a function and the function is minus. Where is he headed? Function's this guy, right? That's going to be my x equals, I think I need to get x by itself. But then what's on the other side? I know this x equals, isn't that x equals, where is it? 0. So I can do x equals this dude minus 0, and then I'm done. But one is, add the x and subtract that. Do you guys get 4 minus 1 minus 2 quantity squared? So I have my r of y, just y, but y minus 0. I have my h of y, my function minus 0, and then I have my 2 pi. Now I heard a lot of you saying, what are our bounds? And you had to think about it. Didn't we just say that this line is x equals 0? And aren't my bounds going to be from the bottom y to the top y? Isn't that when x equals 0? Couldn't I just plug in, take a plus or minus square root of both sides, plus or minus 2, and then add 2, which will be 0 or 4? Done. Right up, but do not solve.
I have 2 questions. So first question is it was a lot easier with the picture, but on the AP, what they give us.
Hey guys.
So the question was,
picture, but
would we get the picture on the AP?
not necessarily.
Okay. Second question is so I was talking to my friends about the shell method, but none of them knew what it was. So I checked the AP curriculum. And it was do they teach it a different way, a different name?
Cylindrical shells. They call it cylindrical shells. I'm not sure if there's any other way of saying it besides shells or cylindrical shells. It could be a topic that a teacher could be saving for the end of the year if they were cut short on time, but otherwise it's a little bit weird. It's a way of simplifying washers, or it's an alternate method to setting up volume, or it's both.
Still kind of confused what you mean by took the radius of the cylinder instead of y.
Because we're in terms of y. So then if you look at the orientation of the cylinder when revolving the para-shell, do you see how it's vertical? And since it's vertical, it needs y variables, heights, in order to define it. So then, whenever I have this representative slice, technically, back from earlier problems in calculus, we sometimes make a representative point to say we're hitting all these different places between y is 0 and y is 4, all those different points on the curve. This y, you have to think about what he is. He's from 0 to the function, which in this case, that's enough to say, oh, hey, that is my radius. But if I was to be revolving about something else, like down here, then I would be taking that y, and I would be needing to do y plus whatever this constant is, or y minus the negative, because then it would be revolving this direction instead. So because the radius is vertical, I'm going to be using y. Maybe it's just y minus 0, and that's sufficient if I'm revolving about the axis. Or maybe it's either like a 5 minus a y, or a y minus a negative 2 to get me my appropriate revolution. But as soon as everything is flipped the other direction, and I have a representative going this way, now my radius is going to be horizontal, so it's going to be using x, with either x minus 0 if it's to the y-axis, or x minus a negative number or a positive number minus x, depending on where my axis is. Okay. Good question. That's one of the hardest ones to visualize. Let me get rid of all this extra, like, hey, it doesn't matter for this problem because that's not the axis of revolution. But that was just a quick reminder of shells. So once again, shells, a way of simplifying washers, and technically, if you get shells down, you'll make fewer mistakes on washers. Or an alternate way of solving for volume. Ultimately, would you be fine and be able to get 5 just as well on an AP if you only knew discs and washers? Yeah. Get a 5 just as well, right? But on an AP, are we ever one to say, like, we'll just miss all those problems? No. I want you guys to be prepared, and I want you to see the content, not only on the AP, but also that a college professor would expect you to use. So discs, washers, shells, cross-sections are kind of the foundation to all of that. That brings us up to section 8.4. Now, I don't think we've graded 8.3, is that right? Someone grab out their homework spiral and have that ready for me. But on Friday, I got you guys these 2 forevers, and did I put them out of order? Oh, I did, and then I forgot to put them back. Oh, I did put them back in order. Arc length. I think I just showed you guys, here it is, I showed you guys the endeavors for arc length, and I think we had these 2 pages up when you guys were leaving class, or at least the endeavor cards. I'm not sure if I had this section over here up. Arc length. In some ways, I could spend forever on it because it does solidify your understanding of accumulation. Because now all of a sudden we're accumulating little baby line segments, and those little baby line segments, kind of like Euler's method, but not, because we're not using tangent lines, but we are using little baby like end-to-end-to-end lines that are getting infinitesimally thin and then accumulating. Oh wait, that's not Euler's. Euler's is an approximation, and it is very much line upon line upon line. But this one, a way of remembering it is, in some way, shape, or form, we are using Pythagorean theorems, hence the square root. Hence the square root of like an a squared plus b squared. But we're using 1 plus f prime of x squared, kind of using the idea of differentials, dy, as opposed to delta y. And realizing that as those distances away become thinner and thinner, as we know integrals do with dx, the error becomes less and less and less, approaching the actual. So in essence, our hypotenuses, hypoteni, have you ever said a plural of hypotenuse? They accumulate, getting infinitesimally thin, they accumulate an actual arc length. But the very, 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 very nice thing that I said on Friday was ultimately, if you can get the formulas down and how to plug and chug, it really is, however the information is given to you, go for it. Now, you guys do see that there is a little r of x in here. And as John asked today, okay, I'm having a little bit of trouble visualizing the r, right? For surfaces of revolution. So maybe that r is still going to give us a little bit of issues. But arc length says, hey, how to figure out how long a curve is. Arc length, yeah, sure, we can figure out arc lengths with circles based on very particular geometric relationships based on inscribed angles and circumference. But if it's anything that's not a circle, how do you do arc length? Well, this is how. An integral of Pythagorean theorem. Integral of Pythagorean theorem where you have 1 plus and you have the derivative being squared. Which derivative? I don't care. The derivative of whatever function in terms of x or y you're given. You don't have to make it match a certain form. Just take it as it is. Take a derivative and plug and check. Just make sure before you integrate it has to be in terms of one variable as we're used to. Surfaces of revolution say, let's take that arc length and let's revolve and then let's accumulate that outer area, that surface area, not the volume on the inside, not pi r squared, but arc length being accumulated with that rotation. There's this thing called a frustum, and we'll see it in a second. It's kind of like a ring and how to figure out the surface area of a ring. But let's start with arc length. Okay, there's this thing called rectifiable. Rectifiable just means there's a finite arc length. Well, if there's a word to describe finite arc length, there must be such a thing as infinite arc length. Gabriel's horn. Anyway, something called rectifiable. I've never seen the AP actually make you use the word rectifiable, but it is snazzy for upper math, and so just let you know that it is a thing. And what it means is that finite arc length and how we can tell it that there is a finite one to even be looking for, that f prime is continuous. Doesn't that mean f is differentiable? Then f is rectifiable. Oh. Well, continuously differentiable, smooth curve, I'm going to have a finite arc length as long as I have finite bounds. Ooh, that means there are infinite bounds to integrals that are coming? This is getting more and more fun. I'm going to go ahead and take away endeavor number 9. You guys saw it on there on Friday, but it's not going to be used in the example on the next page. So let's just focus on endeavor number 8. At one point, I was going to let you guys just look at the work, but let's not. We have time, I think. Has anybody figured out if we've graded 8.3 yet?
We did.
We did on Friday? Okay. We just went over shells a lot and then barely introduced arc length. Are these functions easy to visualize? No. Like, ugh. I don't. Ugh. Oh, I totally just erased the graph of the guy that we're supposed to be looking at. Bummer. We should sue. I mean, not literally sue. Maybe just kind of sue. So what if... Here we go. Now the picture's back. Boop. Okay. What if you had that picture and they said find that arc length? Could you pretend he's a circle and try to do some sort of magic? Yeah. Are we going to? No. Why? Because we know calculus. And it's integral of Pythagorean theorem. Think. Hypotenuse. Okay. Wouldn't be perfect, but would be an approximation. We can make those little hypotenuse, whatever. I was thinking like moose. Maybe it's just hypotenuse, like moose. Because moose is moose. Anyway. I know. I'm sorry. I'm distracted today. Just think integral of Pythagorean theorem. But he's in terms of x. Is that okay? Wait, you can just plug him in? You can just plug him in? Wait, you can't just plug him in. What are we supposed to be plugging into the formula? It's the derivative. So what do you have to do first? And then plug in. And then that's it? No visualization necessary? Besides, 1 to 2. I like these, I think, as long as we can take derivatives. Bring down the 3. 3 over 6 is 1/2 x squared minus, you guys would get a 1 over 2x squared, right? So we just take it and just throw it. Yeah, just take it and throw it in. So therefore, S is arc length and has been arc length for a long time. AJ, I'm going to throw it in the integral. Go ahead. What's your question, kiddo?
I was just like thinking the derivative of 1 over 2x. And I got like 4x.
I did it this way. If you were doing quotient rule, it would be bottom to top, 0. Minus top 2x all over 4x squared. The 2 and the 4 would cancel, so the x and x squared. That makes sense. We have a little negative out there because of quotient. Does anybody see a possible dilemma if you were to have to do this by hand?
Finding the interval about.
Yeah, like I'd have to FOIL, and then I'd have to hope, and maybe a common denominator. Okay. The goal of Chapter 8 test is not to totally kill you on integrals, because that was the goal of Chapter 7. There is such a thing as trig substitution, which in other years, almost every other year, but this year, I've been able to do a quick little module before the final exam and be like, hey, this is what makes some of these crazy integrals possible. Sadly, this year we're not going to be able to. I'll probably throw it up into Google Classroom with like a video that you can see the idea of it, and maybe we'll play with it a little bit the first day we get back. It's not necessary for any problems on the AP. It could be used for a couple integral problems, but it's not necessary. So it's one of those other AP classes might totally cover it and say, this is crucial. I usually just show it, and I'm like, hey, it's a thing, it's cool, it's important. But some of these integrals would be impossible to solve by hand. But the nice thing for us is if it was impossible to solve by hand, it'd be a calculator problem, right? So what does that mean for homework? Make sure you can set it up, and then make sure that plugging into your calculator works. Why? Because the majority of these won't be solving by hand, and technically the point of this chapter is not you solving by hand crazy intervals. Okay? Number 15, how will we set up? You guys see I just took the derivative, plugged in, and squared to like a Pythagorean. Cool. So I would just need to do x prime this time, right? X prime, yeah. Because what integral am I going to do this time? dy. Why? I have y. Oh, okay. 0, 4. Square root of 1 plus. What's messy in these ones is solving the integrals by hand. Well, and taking a derivative, but you guys wouldn't mess that up. Take a derivative, what do you get? This would actually probably be an easier integral to solve, just based on what you think it. But anyway. Can I do a dot, dot, dot? Do you see why I've tried to have you guys write the endeavor cards and be like, just... Because literally, you find derivatives and you throw it in. If we had time on Friday, I would have loved to have done these examples with you, but we just didn't. So can you see how I'm just taking derivatives and throwing it in? We okay? Now, the interesting one on this one, we're not going to make a huge deal about it. If we have a sine of x, they've told us 0 to pi, no big deal. Derivative of sine is cosine. I think you guys have enough information to be like, oh, she just plugged in chug. True?
I think you messed up.
Go ahead.
15. Why is the square root on the bottom?
Because I'm a goof. Which is still a bit as easy. Good. Good. Good, good, good. Actually, it still might be pretty easy, so I think you can just factor it, and then you will get a perfect square, I'm pretty sure. A square, perfect square. Still an easy integral. Actually, easier than but yeah, good cut. Yeah, definitely easier than the previous one. On this one, you guys saw how... Oh, sorry, this is just A and B. A is saying sketch because you might see some weird things in your book problems. Sketch, no big deal. All right, we have the sine curve between 0 and pi. B says find a definite integral that represents the arc length over the indicated interval and observe that you can't solve it yet. How do we solve? U is 1 plus cosine squared. U is What could you do though, guys? Pythagorean property, right? Cosine squared is 1 minus sine squared. But 1 plus 1 is 2. be 1 minus cosine squared to make sine squared. You guys could keep thinking and thinking and thinking. Let me just give you a peek at trig sub, just a peek, just a little baby one, because this one was so easy. Like, oh, we should be able to do it by hand. But I want it to be 1 minus, and it's a 1 plus, so I can't make it sine squared and cross off the square roots and say it's easy. But I could come off to the side and say, wait a minute, haven't I been telling you guys this is a Pythagorean theorem? Or I have a leg, and I have a leg. And I could do a quick a squared plus b squared is c squared, and guess what I would get? And I could do something crazy like, guess what? Tangent of theta is equal to cosine of x over 1. And I could change all of this to be in terms of theta. And I could do something crazy like, okay, well then what would this guy be? Well, wouldn't he be a hypotenuse over adjacent? So I could make this, which is the piece that I really, really, really hate up here. Hypotenuse over adjacent would be a secant. And to get a d theta for dx, for me to even legally be able to do it, I would have to take a derivative, but I'd take this guy's derivative because that just looks gross. And I would get that the derivative of tangent is secant squared theta d theta is equal to negative sine of x dx. And then possibly I'd have to play around a little bit in order to get that d theta in there, and in order to get, wait a minute, but couldn't I say that sine of, how would I get sine of x? That could be a little bit messy. But maybe some of you are seeing, wait a minute, if you can get rid of all of this by just calling it secant theta, and then if you can try to get in this guy, d theta for my dx, maybe I can just take like a really weird trig integral. Trig substitution. It's not that there's trig here, it's that there's some messy Pythagorean theorem relationship here that I could kind of spread out in a triangle and get trig involved and get rid of all the nasty square roots. I'm going to put a quick little dot, 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 because there's a bit more work to be done there. But ultimately, yeah, we'd be plugging in. And we do things like, hey, let's go ahead and get not secant, I apologize. Let's get our theta bounds. Our lower theta bound when x is 0, our upper theta bound when x is pi. For some reason, this sine of x is throwing me for a little bit of a loop. It's not directly in our triangle, because they put trig in here, which is kind of mean. Or else I would show you the simple, it's pretty close to being able to plug in, but not quite. But anyway, this is the idea of trig sub. Is saying, wait a minute, you're a Pythagorean theorem, that means I can draw a triangle, that means I can use the triangle, that means I can get rid of the x's just for a bit and get in terms of theta, kind of like I did with u's, and then maybe everything's possible. Man, I need to ponder that sine of x he's throwing me off. But anyway, that's a quick idea of trig sub, even though I'm so sorry that cosine in there made it a little bit nastier than normal. Usually you don't have trig within trig sub, but long story short. That's if you were doing it by hand, but once again, what did I tell you? Okay, because up there it says you can't do it yet. And so if you guys actually read letter C, it says you can't do it yet. That's letter B, observe. And then C says use the integration capabilities of a grapher to approximate the arc length, aka plug it in. True? Cool. So what's this idea of surfaces? Looks like a dog collar my poor puppy had to wear. He wasn't able to look any part of his body for a bit. Poor man. The cone of shame. The cone of shame. I mean, it's called frustum. It's the key to being able to find surfaces of revolution, because this is a geometric solid with one circular base at one side and a different circular base at the other side, like a trapezoid, and yet not. That can be surface area of which can be solved with a geometry formula, 2 pi r times the slant height. It's a thing. It's a geometric solid. You just haven't always seen it much. A frustum. If frustums are a thing, we can bring it over to a curve and be like, hey, let's use U. But the problem is this frustum uses a line. So we can't just use a geometry plugin because there's a curve where the frustum is a line. But that's okay. I mean, with rectangles with trapezoids. We use linear things, and then the integral just made them infinitesimally thin and perfected it all. And that's exactly what's going on here. 2 pi RL, if that's the surface area of a frustum in geometry, 2 pi radius in terms of whatever, like John asked, we have to orient ourselves with radius. L is just arc length. Plug it in, go. So, geometry solved is not one you see every day at frustum. If we accumulate frustums, making them infinitesimally thin, then this whole little linear, like cutting off of the curve will be just fine. Because the error will be eradicated and our exact surface of revolution will be solved for. We just need arc length to be our slant height, ultimately. And if you're wondering what the dx or the dy is, technically that is just in an awkward way. That's just our I can't say thickness, it's a surface. Lameness is kind of like that whole foot second thing. Dx or dy is based on whichever one you want it to be in terms of. But remember how we said arc length, it doesn't matter? Arc length, it doesn't matter whether you go x or y. Once again, back to that foot second thing. Radius, depending on which way you think of it, it might have to change just a little bit. For instance, if you're looking at this radius, that radius is going to be vertical, aka a height, right? So if that radius is a height and we're having a sliver in space height, which makes it a little bit more awkward, look at that whole sliver in space, that y. If we're doing dy, no stress. It's y, boop, done. But if we're doing dx, wouldn't it have to be y is equal to f of x? Does that make sense? So it depends on whether we're going in terms of x or whether we're going in terms of y as to how exactly we're going to define that r of x. Makes it a little bit nastier as far as application. Guys, I'm going to take this little visualization dude and pop him in front of the Endeavor card so that we can see an example next to our Endeavor card. Here we go. Okay. So what if you took what I said Friday seriously about, it's a formula, plug and chug. And I said, ready, set, okay. Go for this guy. The square root of, 2 square root of x from, it's one of those like use the graph and use the bounds that you see. It's 4 to 9. It's 4 to 9. How would you think of plugging into the formula, knowing that arc length is a part of it, but we also need a 2 pi r times that arc length to be put inside that integral? Let me give you a second. If it is truly just a plug and chug, what would you do? If it is truly just a plug and chug, what would you do? And what would it look like if you had done the y or if you had done that in terms of x? Could it be done either way? Awkward. This is a capital S. Oh, what was the one we just had a second ago?
Small.
What's small s represent? Arc length. What's big S stand for? Oh, we use SA! Or that's nice with a axis, or that's so I don't even know what else it could stand for. Anyway. Slanty asymptote. Ah, there you go. Anyway, S, big S, surface of revolution. What do you guys got? 2 pi integral. Oh, it's 4 and 9. No big deal. Who's your R?
2 and then function.
But why? You'll see it in a second. You'll see it in a second. Did you guys at least do the arc length part right? 2 over 1/2 is just 1, and then aha! Now, Kevin, it's over square root of x, right? And then dx. Did you do the arc length part right? So Ryan's struggling. Ryan, hang in there, bud. Remember the 2 things. Hearing at home helps. How about the y? What would that have looked like? Sadly, not 4 to 9 anymore. But what would have been here? Oh, 0. Not 0. Wouldn't have been 2 root 4 to 2 root 9? See it? You gotta plug in the x's. Lorenzo, hang in there. Don't you have to plug in 4 and 9 to 2 root x to get, well, 2 times 2 is 4, but 2 times 3 is. And then I'd have to do 1 plus, oh, but wait, I need a dy, so don't I need this in terms of y? But wouldn't that just be y over 2 squared? Oh, so y over 2 squared. Oh, I haven't derived it yet? Well, that's a bummer. So there's a lot of work involved, but what is easier? I would end up with a y squared over 4, bringing down to 2. I would have 1/2 y squared dy. Do you see why? How come why, poor k or poor qua, the radius had to be this guy? He's vertical. He's a y. So with dy, which took more work, I could just put in a y. But if I wanted to do in terms of x, it's no stress. I just need to write who y is. Do you see it? Cool. Endeavor card 8, Endeavor card 9. We are done with endeavors. Okay. Yeah, homework is due tomorrow. Here's the dealio. We have options. What do we have this section? We have areas, we have volumes, we have shells, and we have arc length and surfaces, right? Tomorrow's going to be a test review. That test review homework is due on Wednesday with the test. Make sure you have calculators for the test because of what we talked about today. Tonight, don't get totally bogged down in solving everything by hand, but do set up as best you can by hand without graphs or with only what they've given. Good? See you guys later. Thank you.